just one comment. There was a question last time about the notes I talk over. I did try and extract them from OneDrive, and I put them on the Discord page for this course. They are not in a, they somehow came out badly, so I don't think they're of huge use. But if you do want me to keep doing that, please say it, and I'm happy to keep putting them there. If you know how to extract files into PDF form from OneDrive in a better way, please just talk to me afterwards or send me an email, and so I can do it in a better way, but it seems hard to me. The purpose of this lecture is to characterize rigidity, generic rigidity in two-dimensional Euclidean space. So we're at the point where I'm going to think of, for this lecture at least, that rigidity means the rigidity matrix has full rank for some, or equivalently for all generic realizations. And so I'm talking about a graph, and I want to know when that graph is rigid. So I want to have a combinatorial understanding of which graphs are rigid and which ones aren't. And so that's what we're going to do in this lecture. This is particularly the kind of rigidity that I do a lot in my research. So if I go too fast, please do interrupt. If you have any questions, I'll watch the chat, but feel free to shout out and interrupt as well. So as I say, it's going to be about recursive constructions. So what we're going to do is have moves, operations on graphs, and same operations on frameworks. And these operations are going to change a graph by adding one new vertex, and perhaps augmenting the original graph a little bit to allow that. And these are going to be called Henneberg operations, which is where we'll start. And then we'll talk about these operations of building up by adding vertices, and then we'll talk about reducing by deleting vertices, the inverse operations, and we'll use induction to use these operations to prove our characterization of rigidity. We'll talk a little bit about one dimension very briefly as well. Okay, and I should also say I'm going to try and stop talking at 10:02 to allow questions, because several of us have a different thing to go to at, well, I was going to say 4 p.m. UK time, so 11 a.m. in Toronto. Okay, so Henneberg, by the way, was an engineer who published some papers in like 1908 sort of time. So he introduced these operations. I'm using a different sort of naming convention for them, which is 0 extension and soon 1 extension. So first of all, the 0 extension operation. So given a graph, as usual, G equals VE, the 0 extension operation is quite straightforward. So all it does is, as you can see in the picture here, is it adds one new vertex V0 and D incident edges. So of course we always want our graphs to be simple, no multiple edges. So you choose D existing vertices in your graph. So obviously G has to have at least D vertices. You add one new vertex and join it to all D of those vertices. Okay, so that's very simple. The graph G just becomes a subgraph of your new graph, and we typically call the new graph G dash. Okay, and so the corresponding operation on the framework on GP still adds a new vertex V0, but gives it some position, PV0, and the D new edges are D new bars, but it's just exactly what you would expect. Okay, so this is this sort of an elementary operation. I will call it 0 extension, regardless of which dimension it is in. So we will have to keep it in our minds the dimension D, because that's obviously important for how many edges that we put in. Sorry, I think that's MS Teams rather than Zoom notification. Okay. So let's think about this operation straight away. We want to think about why it preserves rigidity. So here's a lemma. I take a framework in RD and I form a new framework from GP by a 0 extension. And so I've used the same letter P, because I'm just doing what I said in the frame, that P of V0 will just be some position for the new vertex. I need to put one small geometric condition on that P. So G dash P is obtained from GP by a 0 extension. It adds V0, as we said, with neighbors V1 up to VD. And the supposition I put on the realization P is that the vectors PV0 up to PVD are in general position. So I don't choose to add PV0 collinear or coincident or anything like that with the neighbors of it. It could have been added coincident to some vertex it's not adjacent to. I will allow that sort of thing, but it just has to be in general position with respect to the D neighbors of it. Okay. So then the conclusion of the lemma is that the rank of the rigidity matrix of the graph you get after you've done the zero extension is exactly D more than the rank of the rigidity matrix you started with. So I'm not assuming that GP is rigid or anything particular about its rank. It's whatever its rank is, I add D to the rank when I do this operation. So it's more general lemma than saying rigid to rigid. The fact that adding D would preserve rigidity is a special case of this lemma. When the rank here was full, then the rank here would be full. Okay. So the proof is very easy. Maybe I didn't need to write anything if you're familiar with the rigidity matrix. What happens is when I take the rigidity matrix of G dash, I can just write the rigidity matrix of G and add the D columns for V0 and the D rows for the D edges incident to V0 and get a square submatrix in the bottom right that importantly has zeros above it everywhere over here. So that clearly the rank of Rg dash P is equal to the rank of RGP plus the rank of the D by D submatrix in the bottom right. And then the general position assumption on vertices V0, positions of PV0 up to PVD, ensures that this bottom right block is invertible. And so it does have rank D. And so we do add D to the rank to get the result. So there's a couple of comments in the chat. So we can have a highly non-generic rigid framework in zero extension still preserves rigidity. Yeah, so however generic or non-generic the thing is, if it has the rank K, then the zero extension under the supposition of general position for those vertices that were involved, we do add D to it. So if it was rigid to start with, however non-generic it will be rigid afterwards, yes. Yes, yes. So thanks for the answers to that in the chat as well. Okay, so let's look at a second operation. So this time, it's not going to be quite so easy because this time we're going to augment the first graph. So in particular, we start with a graph G, and we start with a specific edge in the graph. So let's say between V1 and V2. And again, we need to have a certain number of vertices in the graph for this to matter, because we want to have D minus 1 additional vertices as well. So G must have at least D plus 1 vertices, and it must have at least one edge. Okay. So the one extension now, by the way, the 0 in zero extension was because we deleted 0 edges. The 1 in 1 extension is because we're going to delete one edge. We're going to delete this V1, V2 edge. So that's why it's 0 and 1 rather than 1 and 2, say, or 2 and 3, or D and D plus 1 or whatever. It's 0 and 1 because it's the number of edges we delete. So we define the one extension operation, and if you want to be very specific, on the edge V1, V2. So again, we add one new vertex and we call it V0. This time we remove the edge V1, V2. And now we want to add D plus 1 new edges. So V0 will be adjacent to the two endpoints of the edge we removed. So it's adjacent to V1 and V2, and it's adjacent to D minus 1 additional vertices, which I've just labeled as V3 up to VD plus 1. Okay, and then the framework operation, I'm going to be maybe slightly unusual compared to what I would usually do. I'm going to specifically say that the framework operation imports some geometry in it. So the corresponding operation on the framework adds a new vertex V0, and we position it at PV0, but I tell you PV0 and it's something particular. So PV0 is chosen to subdivide the bar between PV1 and PV2. So I'm inserting it and deliberately making PV1, PV0, PV2 collinear, okay? And then I insert the D minus 1 additional bars from PV0 to PV3, PV4, etc., down to PVD plus 1. Okay, so here's a picture. So as we've seen, hopefully it's relatively clear, but just to double check, here's the edge V1, V2. We're going to delete that edge, subdivide it, add V0 to V1 and V2 as a nice little collinear triangle, and then we take d minus 1 additional vertices and join it to those. So for example, in dimension 2, it's only one additional vertex, and so V0 would be a degree 3 vertex if we were talking in 2 dimensions. Okay, so that's going from G to G dash, and really I've drawn it as if it's the framework going from GP to G dash P. Okay. So, I mean, I've just said this, but the new framework will be non-generic because of this collinearity. This is okay because what we're going to do is show that at this non-generic realization with these 3 vertices collinear, we add the maximum possible to the rank we could, and hence when we move to any nearby generic position or any generic position at all, the rank won't go down. So if we can prove rigidity is preserved at this special position, it will guarantee that rigidity is also preserved by a generic framework. So if we have a generic framework G, which is rigid, and we apply this move at the special position, it will be rigid, and then at the generic one, it will be rigid as an immediate consequence. So let's look at the lemma that proves this operation preserves rigidity. So here's the statement. So again, we've got a framework in RD, GP, and we let G dash P be obtained from GP by the 1 extension. So in particular in G dash P, the PV0, PV1, and PV2 are all in collinear. Everything else is as it was in GP. And again, we make a general position assumption. So there are no collinearities or coincidences, etc. among the vertices V1, V2 up to Vd plus 1. So we know PV0 is collinear with PV1 and PV2, so it's not in general position. But the d plus 1 neighbors of V0 are all nicely spread around. They're not, there's no collinearities there. And really this assumption is because we're going to use the previous lemma. We're going to use the fact that 0 extension works in our proof. And then the conclusion is the same as before. I've written in the generality that the rank of the rigidity matrix increases by d. So if GP happened to be rigid, whatever generic or non-generic it was, then G dash P, subject to this general position condition, has d extra to its rank, and so it's rigid as well. So in particular, this does show rigidity is preserved, but it also says whatever amount of flexibility you have essentially the same amount after you've done the move. Okay, so we want to prove this. So the first thing I'm going to do is we're going to look directly at these 3 vertices that are collinear, V0, V1, and V2. So in particular, I want to just forget the rest of the graph completely exists and just imagine you have a complete graph on 3 vertices that are realized with this collinearity. So my graph is K3, so it's just this. It has the 3 vertices V0, V1, V2, and I've realized them collinear. In particular, I've actually choose to put V0 on the midpoint. You could put it anywhere along the line you like, but this is one choice. And what I want to show is that this is essentially a circuit. So the rigidity matrix rows are a minimal dependent set. So why is that? Well, let's write out the rigidity matrix. This is just writing it out in full. But when we make this substitution, because we know that PV0 is on the line through PV1 and PV2, in particular it's at the midpoint, then this translates into this matrix. And then if you stare at this matrix for more than a couple of seconds, I think you'll see that this has rank 2, but it also has the property that any 2 of the rows are linearly independent. So it's a dependent set of rows, but it's minimally dependent in the sense that if you take any one of those 3 rows away, it will still have rank 2. Okay. So
it means a circuit in the matroid, you said?
Yeah, so it's a circuit in the rigidity matroid, yes. So, but I try and want to not use matroid terminology unless I need to. So it's a minimally dependent set of rows in the rigidity matrix. Okay. So now we know that this triangle, remember, it doesn't exist in G because V0 doesn't exist, and it doesn't exist in G dash because V1, V2 doesn't exist. But still, I'm going to make use of this because we're going to have a a sequence of graphs like this. So on the left, this is G that we started with. On the right, here is G dash, which we want to finish the move with. And in the middle, I don't have the collinear triangle either. Notice these are graph pictures. I haven't drawn them collinearly. But in the middle, what I've done is I've taken G dash and I've added back the edge V1, V2, and I've deleted the edge from V0 to V2. Okay? So in other words, G dash is formed from G by adding a vertex V0 and D incident edges. So it's adjacent to V1 up to VD plus 1, but it misses V2. So G dash plus V1, V2 minus V0, V2, this graph in the middle is formed from G by a 0 extension, which adds V0. So because it's obtained from a 0 extension, the lemma before tells us that this graph, which maybe I should have given a name to, it does increase the rank by D. Okay. So now what we want to do, we know this graph in the middle is rigid. Say if the first one was rigid, it has the rank we want. What I want to do is take the edge from V1 to V2, delete it, and add the edge from V0 to V2 to move to this one on the right. So that swap of edges, and I claim, and I'll show you in a moment, that swap of edges is okay because exactly what we said about the K3 realized collinearly being a circuit, being a minimal dependence set, because it was when we add, so let's say we're in the middle blue blob, if I add V0, V2, because I'm adding it when these three vertices in the framework are collinear, I don't increase the rank, and then that set of three vertices gives me a minimal dependence set, so I can take the edge V1, V2 away without changing the rank as well. And so I do preserve the rank when I go from there to there. I guess to see this, you probably need to think about the K3 as the submatrix for K3 is a submatrix of the full rigidity matrix. But if you think for a second, you'll see the extra columns don't have any effect on that little minimal linear dependence because they don't have entries for that triangle otherwise. So that's okay. So let's see it written down. So here's the calculation. So as I said, since this calculation we just did for K3, told us that our special realization of the vertices V0, V1, V2 gives us a minimal dependence set. Of course, a generic or a general position realization of K3 is independent, so it wouldn't have worked in general. We'd have had to have found a different argument. But with the three vertices collinear, we found this minimal dependence set. And as I just said, so now, well, I mean, what's here, you really need to see the picture there, but hopefully it was up enough to spot it that the resulting graph we want, its rank is going to be the same as what we get from adding V1, V2. So that's of this graph with that blue edge, which is the same as we get by deleting V0, V2, which is this one by the collinear triangle property, which was the same as the first thing plus a 0 extension, which added D. So I'm sorry you can't quite see all of that at the same place, but at least it's clear to me. So I hope if no one asked a question that means it was clear to all of you. So suppose we had a rigid thing, then it's rigid after this move.
Tony, I'm not quite seeing this last step where you kind of swap edges,
Okay.
why that preserves the rank.
So maybe I try again. So you were happy that this graph had rank D higher than this one?
Yes.
Okay, and then so I have these three vertices here, and so now it's V0 here, but V2, this one doesn't exist, but this one does. And so within this little collinear triangle, so suppose it was rigid to start with, then this graph had full rank, so adding this edge clearly can't have any effect. It must be dependent because we have the upper bound on the rank and we've achieved it. But now we know that this triangle is a minimal dependent set, and since it's a minimal dependent set, a circuit, doesn't matter which of the three edges we remove, we won't affect the rank. So when we remove this one, the rank will not go down. and hence we'll get to this one and still have the rank we want. And then if you're happy with that, then the fact I generalize it, so I'm not starting with rigid. You use the dependence to say that when you added this one here, the rank doesn't go up as well. How's that?
I see. It's so the reason that adding back in the edge doesn't change the rank was because of the circuit property.
Yes.
But you can see that circuit property independent of the rest of the graph. That's the thing that was bothering me. But here I see that because the rest of the graph doesn't involve, well, it does involve V0 though, right? I mean, there's lots of edges that connect to V0. So I don't quite see why you know that this is not increasing the rank.
So I mean, it is back to this thing. So essentially, you have two of these free rows in your matrix. Okay, there's a lot of extra stuff because there's lots of extra vertices and then extra rows underneath. But you have this here, and these rows are all zeros because the vertices aren't affected here. So you have two of these free rows. Say it was those two, and you have one more row, and this depends on those, so it can't increase the rank.
It was really this all zeros business that was bothering me, but now I see it. Okay, great.
Yes, so because this is V1, this is V2, and this is V0, I hope that's the right way around. All these vertices have no effect on the rows, and so there's lots of zeros over here. So it extends directly from the small matrix I showed to the full thing.
Got it. Yeah, of course. So it's the structure of the rigidity matrix that's important here. Okay, great.
Yes. Yes.
Wait, now I'm confused because I thought V0 is also connected to other vertices.
So it is, but so let's make some space.
But that's in a different, that's.
Oh, the rows are the
another
edges.
column.
Rows are edges. Got it.
Yeah,
Sorry.
that was the thing I missed too.
Yeah, so V0 has lots of entries in its column, D+1 different rows with non-zero entries, but in any particular row, it's only the things it's adjacent to. So there would just be lots of zeros in those particular free rows. This is a really important point, actually, so I'm glad people are asking questions, because this kind of special position trick really works well for one extension, but it really doesn't work in really important open problems in rigidity theory. So being sure of it is about why it works is really useful, I hope, for anyone who's new to the subject.
So could I summarize it by the fact
Sure.
that one extension does this well is the zero extension property, increasing rank, and additionally this moving around in this little cycle, this circuit of the matrix. Okay.
Exactly, yes.
I have a quick question. So this seems to be, I guess, a common technique because we also saw it in Bill Jackson's lecture for a different operation. But it seems to be like highly dependent on finding a circuit and in the dimension that you want. So are there any techniques that kind of avoid this? Because I guess my question is, would it be an obstacle for proving it in like arbitrary dimension because you couldn't find, a circuit for every dimension very easily? I mean, for more complicated operations as well.
Exactly. So yeah, it's just maybe I can just spend a minute or two on this. So there's a very important operation in rigidity is called X replacement, where you take two. I think I'm going to talk about this at some point, but maybe I can just not talk about it as much next time when it comes up. So this one would delete two edges, and I've drawn them looking like an X. So they have four distinct vertices. So it's two non-incident edges, and you insert a new one like this. And in 2 dimensions, you can do a similar proof to what I've just done, because you can take the midpoint where the two lines through the two edges intersect, and you can make 2 collinear triangles. But when you try and do this operation in higher dimensions, so say in 3 dimensions, your 2 lines through the 2 edges need not intersect. So finding a circuit for that, and that's a completely open problem. So doing this operation, this X replacement operation, which we'll come back to in 3D, where the new vertex has degree 5, but you can't make these two circuits, is suddenly a really difficult thing that people don't know how to solve. You can do the one extension argument in different ways. So there are, let me just explain one way, and let me just do it quickly. So again, I want some space. So this is an argument that, oh, that didn't work. Sorry. Okay, so remember you're deleting this edge and you're then adding this. And let's just say we're in 2 dimensions to make it easy. So we're doing this operation. And this was V1, V2, V1, V2, V0. So one way to do it is to argue by contradiction. So you put your new V0 in and suppose that the framework you get is flexible. Suppose it has an infinitesimal motion. One way you can do it is by considering a sequence of frameworks where, and you have to be slightly careful in how you do this, but where V0, the position of V0 tends to V1. So you have frameworks G dash P, let's say P1, G dash P2, P3, 4, is you have a sequence of them. And as that sequence tends to infinity, PV0 gets closer and closer to PV1. And you can use this sort of limiting sequence and the properties of it to establish a contradiction by showing that the infinitesimal flex must transfer to this framework. So it was in a slightly different context, but I did this in a paper with Stephen Power and with John Owen in 2012. And so
though you're drawing V0 is not collinear, you're actually thinking that it is collinear in the realization.
Right. Sorry, no, this is a completely different argument. So in this one, this was just this was say a generic framework where V0 was put not collinear with V1 and V2. It just was put somewhere nice and general. And then you start from that general one and have a sequence where it moves closer and closer to V1. So it didn't have the special position thing. That was a completely different argument. Sorry, I didn't make that clear. And there's another kind of argument where you use the algebraic independence, which basically means you write down the polynomial equations you get for the lengths for this edge, and this edge, and you just try and solve them, and you use what you know about the framework to develop information about the length of this edge, and you start algebraic manipulations. There's probably other techniques for proving this move. Maybe none are occurring to me right now, but yes, there are other ways of proving it, but none that apply to this big open problem as far as I know.
Okay, thanks.
Okay, great.
Is that X move, is it also a 2 extension?
Yes, so a 2 extension, I mean, it slightly depends. So when I say X move, these 4 vertices were distinct. You could have had the 2 edges like this. Then I call it a V replacement. So I forget if 2 extension is just this one or if it's actually both are covered by that. So okay, I separate them out because the V extension move is weird because it doesn't necessarily preserve rigidity. Whereas the X move, at least in the plane, does, and in free space we conjecture it does. At least I hope I'm not alone in believing it does work. We just can't prove it.
Tony, the graph that you have right below the X, is that only working in R2?
This argument?
Yes.
Okay, so the paper I'm talking about, we used it to, so suppose you have some nice smooth surface that you fix in R3, and you realize the points of the framework on that surface, and so your rigidity, you constrain your graph or your framework to lie on that surface. So the context we did it in was in that. So the sort of the limiting argument was a bit complicated because you have to use the curvature of the surface as well. So I guess we never wrote it down for 2-dimensional Euclidean space, but I claim the dimension shouldn't matter in Euclidean space. I claim that same argument is not just a 2-dimensional one. It would work in D. Of course, this wouldn't be a degree 3, it would be a degree D+1. But the only important things, I think, were that you tend it to one neighbor of the removed edge. So this edge, the third one, or the fourth, fifth, sixth, whatever dimension you're in, I think just come along for the ride, and you just need the right number for the rank to go up by the right amount, and basically a zero extension for it to be okay. So I think it works in D dimensions, but it's not formally written down anywhere. Was that clear?
What's the statement you're trying to prove? That this preserves rank or increases rank by D?
Yes. Yeah.
But you don't need V0 to be collinear anymore, whereas we needed it
Correct.
before.
So before we used the fact that V0 was collinear simply to make the proof work. We really cared about the generic move from one to the other. And so in both cases, what I really care about is that if G is generic realization of G is rigid, or say is rank K, then the generic realization of G dash is rigid, or say rank K plus D. And so that this version, I claim, proves the same thing.
Okay, so this is proving the same result, but not using collinearity at all.
Exactly.
Okay, thanks.
Okay, so I think we're done with the questions. So this is basically a little summary lemma, corollary, and this is what we're going to use. So we talked about moving the rank up by D. So suppose now that your graph is rigid, or say minimally rigid even, and let G dash be obtained from it by a sequence of these extensions. So it doesn't have to be just one of these operations, but you can do a 0 extension, then 2 1 extensions, then 4 0 extensions, and so on. Then just applying these lemmas repeatedly and moving to a generic positions, then you will find that the result is rigid or minimally rigid in R2. So we always preserve the right count. So by preserving rigidity, the minimal comes along for the ride as well. So what we know is that every graph you can generate, if you can prove some small graph is rigid, every graph you can generate from it by sequences of these operations will also be rigid. And that's the sort of linear algebra geometric result we will need. And then the rest of this lecture will be purely about graphs, using this corollary to prove the rigidity characterization.
Sorry, could you just remind, what does minimally rigid mean again?
Okay, so rigid in this lecture, I'm taking to mean that the rank of the rigidity matrix is equal to D mod V minus D plus 1 choose 2. We talked about this being equivalent to continuous rigidity in terms of continuous motions and things, but for now, rigid means this, and minimally rigid means this plus the rows of the rigidity matrix are linearly independent. So this is equal to the number of edges. So I want to have it to be rigid, but if I delete any one edge, I reduce the rank. So formally, I say minimally rigid means rigid, but G minus E is not rigid for any possible edge E, and hence all the rows of the rigidity matrix have to be linearly independent, because every single one, if you just take it away on its own, must reduce the rank. So I take it to mean the rank is equal to this, but that's also the number of edges.
Okay, so it's a full row rank. Okay.
Yes.
Thank you. Sorry.
Okay, so I guess it's very unlikely I'm going to get finished proving the two-dimensional thing, but I wanted to get as far as I can towards it. And I think I'm going to mention one dimension first as well. So to do some graph theory, instead of 0 extension and 1 extension, going the other way when you reduce the number of vertices, I'm going to call them 0 reduction and 1 reduction. So 0 reduction is simply the removal of a vertex of degree D from a graph. Take any vertex of degree D, take it away. This is the graph you get from applying a 0 reduction. A 1 reduction, now it's not quite the inverse, but it is the reverse operation. So a 1 reduction removes a vertex of degree D plus 1, and say it has neighbors V1 up to VD, and then it adds an edge. But now there are lots of possible edges because it's just some edge among these vertices gets added in. So you can see there's lots of choice in and lots of options for how you would do a 1 reduction. So that's a bit different. Okay, so let's just very briefly mention the one-dimensional case. And so if anyone knows specifically who I should credit for this, then please shout. But the one-dimensional theorem is that a framework, and now I don't really even care about generic, a framework in one dimension is rigid if and only if its underlying graph is connected. So in some sense, I've done most of the proof of this, but I'm leaving using you can use the operations above if you like. If anyone's doing this course for credit and wants to have some exercises to do, I've sprinkled some throughout the notes. This is one example where you might have a go. You can phrase this rigidity characterization in terms of minimal rigidity instead. So that would be saying that minimally rigid graphs are connected graphs, but if you delete any edge, it becomes disconnected. So it's exactly trees. So it has to span this vertex set of your connected graph, but it's just G as a tree itself. Okay, so that is easy, I hope. But in some sense, it's nice as well, because it's saying, here's this geometric thing about rigidity, which characterizes graph connectivity. So if we change the dimension, what do we generalize graph connectivity to? So this is maybe a motivation for combinatorial people to study rigidity. So in 2 dimensions, it's going to be harder, and it might take the first half of the next lecture, I guess. So I need some notation. So first of all, G square brackets X is the subgraph of G induced by X. So you take some subset of your vertex set and all the edges that are between pairs of vertices in X. And this gives you some graph. I'm going to use D to denote the degree of a vertex. Delta is the minimum degree. Capital N is for the neighborhood or the neighbor set of a given vertex. And then I guess the only maybe one you might not have seen before is dx comma y is the number of edges between x and y. So if I have 2 sets of vertices, x and y, it's the number of edges like this. So it's the number of edges with one endpoint in x not y and the other endpoint in y not x for 2 subsets of vertices. So this is just some basic notation that's going to make things a bit easier. Okay. Okay, so last time we talked about the necessary conditions. And so we know that we want to look at this d mod v minus d plus 1 choose 2, which when d is 2, this is 2v minus 3. So let's define that class of graphs. So in particular, what I want to do is say that a graph is called 2 free sparse. Remember, I of x was the number of edges in the subgraph induced by x. So you take any subset of the vertex set, your graph is 2 free sparse if for all possible choices of x, you have at most 2x minus 3, except that there's one exception. If you have a single vertex, then obviously a single vertex has 0 edges, but you have 2 times 1 minus 3 is negative. So you have to not worry about that. So you only check all subsets with at least 2 vertices in. Okay. So you're 2 free sparse if you always satisfy this inequality. But for example, any tree satisfies this. So it's nowhere near what you would need to be minimally rigid in general. But if you have this and you also tell me about the total number of edges in your graph, so you say the total number of edges actually hits equality in the Maxwell counting that we had on Monday, then we call the graph 2 free tight. Okay. So it's 2 free tight if it has E equals 2v minus 3, and every subset of the edge set satisfies this inequality. Okay, so let's see some examples. So as I say, so you can be 2 free sparse and flexible. You don't need to have the right number for rigidity. So if you check, for example, the 4 cycle there, so it's got 4 edges and 4 vertices. So clearly E is less than 2v minus 3 if you go through it. You can check, and you have to check all possible subsets x of v. So probably you don't have time to check every single one in the examples I'm doing. I'm just trying to give you an impression of them. This one is a 2 free tight graph. So is this one. So you can see that really from here to here, I just applied 2 zero extensions in a row. So I first added this vertex of degree 2, and then I added this vertex of degree 2. So in 2 dimensions, a zero extension adds degree 2. And so from here to here is just a natural zero extension operations. And then here's one that's not sparse. So this is not sparse because it has too many edges. So this has one too many edges for this condition, but it's also not sparse for a second reason, because K4 has 6, which is greater than 2 times 4 minus 3. So it has a bad subgraph as well. If you deleted one of the edges from the K4, then it would be back to this graph, and you would see it. So it has a spanning 2 free tight subgraph just by deleting, say, this edge, but oops, that's not good. But you could also have examples where, so this one would be a different example. So this one it satisfies this count. It has E equals 2v minus 3, but it's still not sparse because it still has the K4 subgraph. So this one, you can sort of see this as a quite nice example, because it sort of shows you a bit, at least in my head, it shows some intuition of why these graphs are the ones that correspond to rigidity, because here it's like the one on the left of it, but I took one edge, this one, and put it over here instead. So I've sort of spread the edges badly around in the graph. So I've spread them from a nice rigid organization to a flexible one where the 4 cycle moves, and there's too much redundancy over here in the K4. So you can sort of see how the 2 free tight condition is sort of related to the rigidity condition. Okay, so hopefully everyone's happy with this class of graphs. So here's a couple of exercises. I mean, you can just take these as facts that aren't so hard to prove, but feel free to have a go and ask me if you didn't manage, or you want me to check what you did. So the first one is, suppose I have a 2 free sparse graph G, and I form a new graph by a 0 or 1 extension. Prove the result is 2 free sparse. So I hope in the 0 extension case, this is basically trivial, but in the 1 extension case, there is a little bit to check, but hopefully it's not difficult for you. And the second one is just giving a combinatorial property that 2 free tight graphs must satisfy. So suppose this time you're tight, so G is 2 free tight, prove that it must be 2 connected. And so 2 connected, I mean in a vertex sense. So 2 connected means there is no vertex that if you remove that vertex, your graph breaks up into multiple connected components. So it does not look like this. There is no vertex V such that G minus V is disconnected. So there's, I mean, and number 2 is sort of a little counting argument. So hopefully they're okay. Now, so I'm going to spend 5 minutes trying to build up towards the proof of Lemma's theorem. So this will just all be a couple of combinatorial lemmas, I guess. So the first one, hopefully, again, is relatively easy. I pick a graph, any graph, and 2 subsets X and Y of its vertex sets. Then I claim this equation is true. And so really, I just want to count the contribution to both sides. So I look at the number of edges in X, I look at the number of edges in Y, and I look at the number of edges between X and Y. And I claim I get the same thing as if I counted the number of edges in the union, which got all these, plus the number of edges in the intersection, which got these. And so you can see from my, I mean, if you can still see it, but you can see that the 2 colors I used on the left and the 2 colors I used on the right match up in the right places. So this is a triviality. But we'll use this equation, I guess, a few times in what follows.
So I of a subset of vertices is the number of edges?
Yes.
Okay.
Yes, so I take the sub X as a subset of V. I look at the graph G induced by X. I of X is the number of edges of this thing. Okay, so yeah, I was saying that if we take a subset X, I'm going to call it critical if it achieves equality. So they're critical because these are the sets that can cause problems. So imagine in your graph, you have a set like this, X, and it contains V1 and V2, and I want to do a 1 reduction that deletes V0 and adds this edge. Then because I achieved equality, when I add one more edge in, then equality will become this way around, and I will violate the two free sparse condition. So they're critical, and what I'm meaning is they're the sets that can prevent me from doing one of the reductions I want to do. So these are the blockers to the combinatorics being really nice. These are the ones that mean you have to do a little bit of work to make it happen. Okay, so it's also true that what we're going to have to worry about is intersections and unions of these sets, and in particular intersections and unions of these critical sets. So probably I have time to prove this in the last 3 minutes. So suppose I have a two free sparse graph G, and I take two critical sets X and Y. And you'll see this condition that they need to intersect at least two vertices in the proof. It basically boils down to the thing I said, that the two free sparse condition you don't apply to single vertices, because a single vertex has 2 times 1 minus 3. I mean, it obviously has 0 edges, so this is bad. But we have to do something different for single vertices. But if we have critical sets that intersect in at least 2 places, then the intersection and the union are both critical, and there are no edges between them. So the two sets look like this, and there's no edge of this form going around from one to the other. Okay, so how do we prove this? X and Y are critical, so I of X is 2x minus 3, I of Y is 2y minus 3, that's just by definition. X union Y is a subset of V, so clearly we have at most the number you can have, just by two free sparsity. And the intersection, again, is a subset. And because the intersection has this condition, we have this. If we didn't assume the intersection was at least 2, then from what's happening here, you could put a 2 there instead, which would cause problems. But we can't do that because we've made this assumption on the intersection. So now we just do the equality in the previous lemma, which was I of X plus I of Y is I of X plus I union. Ix intersect plus union, and I've put the minus dxy on the other side, but that's what we're going to use, and just could count up using the things I've written down. So I of X was 2x minus 3, because it's critical. I of Y is 2y minus 3, because it's critical. The previous little counting lemma. The intersection is just about to go off up here. That's at most this. The union is at most this, and we still have the dxy. So again, there's nothing much has happened there. The size of X plus the size of Y is the size of X intersect Y plus the size of X union Y. So we get this equation. But now if you look at the start here, that's less than or equal to this. And since it's less than or equal to this, it must be the case that dxy is 0, because otherwise they're the same. And it was being subtracted. And hence that's 0, and hence they're the same thing. So the inequality is actually an equality, which means the equalities we had here and here are actually equalities. And since they're equalities, we know that the intersection and the union are both critical as well, which is what we were claiming in the lemma. Okay, so I am out of time, so I won't go any further, but just to give you the sort of the basic hint, the idea is that we're going to use this when we're talking about a vertex of degree 3, and we want to reduce it by a 1 reduction. So we want to add either that edge or that edge or that edge. And it might be a critical set blocks us here and a critical set blocks us here, and this is X and Y. And we use this union intersection lemma to understand what goes on in this kind of situation. So we're going to use this in the first half of the next lemma, just to work combinatorially with these two free tight and two free sparse graphs to establish that the 0 reduction and 1 reduction are enough to get all two free tight graphs by a recursive construction. But we'll go into the details of that on Friday. And so I'll stop in case there's any questions at this point.
I had a question. So the critical sets are the ones from for the one extension that we need to be careful that we don't add an edge to, right? Because then we'd have a subgraph violating the inequality.
Exactly, yes.
Okay.
I'll create a little space so that's gone wrong over here, but let's just get rid of that. Yes, so exactly what you said. So we're going to have a vertex of degree 3, say it has neighbors X, Y, and Z, and I'll go into this in more detail next time, but suppose the 1 reduction I try and do adds the edge X, Y. So the only thing that can go wrong is if in the small graph over here, when we've done the reduction, there is some set containing x and y, which has I of that set. So let's say it's a z, which has I of z is greater than 2z minus 3. Because if this doesn't happen, it satisfies the sparsity condition. Because if there's no such graph like this, no such set like this, then every other set anywhere else is a subset of the one on the left. And so but this subgraph I've circled z, the subset z, has one more edge than it did in the previous one. So it must actually be equal to 2z minus 2. And hence over here, z without the edge xy, and now it's induced, z is being induced in the smaller graph, has I of z equals 2z minus 3. So it's exactly a critical set. So yeah, they're exactly the problems we have to worry about to show that we can find some reduction at a degree free vertex V.
Okay, and then dxy, was that the intersection of x and y, or
so dxy was, so you have your set x and your set y, and so in the union could induce edges of this form. So dxy is exactly this. So it's edges with one end vertex in x not y and the other end vertex in y not x. So it's edges that go around like this. It's not anything to do with in here, or it's not edges in here or edges in here. It's only ones with an end vertex on one side and another end vertex on the other side.
Okay, so this is just saying that the union of critical sets don't have edges between the two critical sets. This lemma, I mean, is that what it's saying?
It says the union of two critical sets has no edges, but is critical and has no edges between them under this assumption. It is possible that your two critical sets do intersect in exactly one vertex, and there is one edge between them. That's a possibility. But if you assume at least two vertices, then yes. So we have to worry about this case on Friday. But with this assumption, what you said is exactly right.
Okay, thanks.
So may I ask another question in curiosity? Sure. Is if how does it work for dimension 3? This is will there be is there anything of that kind in dimension 3, like the target of the next lecture?
Yes, so let me make some space. So I'm going to go into this I'll be brief because I'm going to go into this in future lectures. We're going to talk a lot about dimension 3. So in dimension 3, you'd be talking about this, and you'd be talking about this kind of inequality. So this would be the analog of 2 3 tight would be 3 6. But I mean, I can say many things. So the first thing is that some of these graphs are flexible. So the 2 3 tight graphs are all rigid. That's what we're trying to prove and what we'll finish proving on Friday. But the corresponding necessary condition in 3D is not sufficient. So you need to know something much more complicated that we don't know. It's actually an open problem to work out which ones are rigid. So some of these graphs are bad, and it's can be bad in very subtle ways. In terms of what I'm actually doing with these 0 extensions and 1 extensions, as we showed, the fact that they preserve rigidity works in d dimensions, but the combinatorics coming down, the point is they're not sufficient. So in 2 dimensions, what we're going to show is that all 2 3 tight graphs can be generated using just these 2 operations, but in 3D that becomes false. So you can still do reductions using them when vertices of degree 3 and 4 exist in 3 dimensions, but you can't get everything. There are graphs you cannot obtain using just those moves. So you need to have new operations that make it more complicated. And the fact the class of graphs you're looking for is not the right one anymore. You need to edit this, and even having a conjecture for what the change to that would be is a hard problem. So it's just, everything becomes much more complicated in higher dimensions, I guess. But I will talk about that in detail in some lectures.